Welcome back everyone. In the last lecture I have explained you what PID controllers are, and I have also given you an intuitive feeling as to when to use a I controller, when to use a D part or the PD controller and the PI controllers. Today we look into methods by which you can find out the values of Kp, Ki and Kd. Remember, if you know the transfer function of a system, you know how to find out the value of Kp, Ki, Kd, right? Because if you know the transfer function of a system, and of course, if you know the objectives, performance objectives, we can always find out the value of Kp, Ki, Kd using the method that we have seen in two of the lectures before this, in which we took example of the quad rotor and we also took a system like 1 by s plus 2 into s plus 4, where 40% overshoot and 2 second settling time was our objective. So, using that also you can find out the value of Kp, Ki, Kd. Okay. Now, instead of that, suppose if you have a system where you do not have any specifications as such, you just have a system, then how do I tune the system? How do I know what should be the value of Kp, Ki, Kd? And there are methods to find those. Let us have a look at that. Remember, tuning of PID controllers means that I have to find out the value of Kp, Ki and Kd. This is what tuning of PID controller means. Now, there can be two cases. The first case is that the dynamic model of the plant is not known. That means you do not know the transfer function of the system, you do not have any idea about the transfer function of the system, or maybe you do not have time to do that, you just want to come up with a controller that helps you getting to your objective. On the other hand, there can be a case where you know the transfer function of the system. Let us look at the case when we do not know the transfer function of the system first. Now, suppose you do not know the transfer function of the system, then you can have two cases again. One can be that the step response of the plant is an S-shaped curve. So, that means what it says is that you find out the open loop transfer function, you take the open loop transfer function GSHS and see what is the step response of this system. Okay. And if the step response of this system comes out to be something like this, an S curve, okay, then you can go ahead and apply these methods that we will talk about. If you do not have a S curve, then generally there is no specific tuning method. So, then you will have to maybe struggle a bit, but in most of the cases I think it generally comes out to be an S curve, for CISO cases at least. So, now if you have an S-shaped curve, remember, okay, again let me just again emphasize, what are we trying to do? We are trying to find out the value of Kp, Ki, Kd. Then always you can ask the question, oh, if I have to find out the value of Kp, Ki, Kd, previously we have seen that I have the transfer function and I have the objectives. I have to convert the objectives into desired pole locations, and once I have the desired pole locations, I have to draw the root locus of the open loop transfer function and see whether the root locus passes through the desired location. If the root locus does not pass through the desired location, then I maybe design a PD controller or a PID controller depending on the problem, and then once I have designed a controller, I adjust the gain such that I reach to that location. This was the method that we have till now done. Suppose you do not have an objective at all. Suppose you just have a motor and you want to control the speed of the motor. There is no specification as such. You have not put any specifications. You can go for transfer function, you can find out the transfer function and you can put your arbitrary specification and go ahead and tune the system. But suppose you do not want to do that, you do not want to find out the transfer function, you do not have to find out the transfer function, okay, in that case. So, what you can do is you can look at the transfer function of the system and then check whether the open loop transfer function step response gives you an S curve or not. If it gives you an S curve, then you can go for what is known as Ziegler-Nichols method. Ziegler-Nichols came up with these methods, okay, and there are generally two variation of the method. One is called an open loop method and one is called a closed loop method. We will look at both the variation. So, let us look at the open loop method. Now, what is the open loop method? Suppose this is the step response of your system, okay, of your open loop transfer function. So, if this is the step response of your open loop transfer function, then first thing is that you find out an inflection point on this plot. Now, what is an inflection point? Inflection point, this is the inflection point, okay, and at that point you draw a tangent, okay. So, you draw a tangent at that inflection point. So, once you have drawn the tangent will cut the x axis at a point, okay, and this is the maximum value. What is this called? This had a name, right? This is the steady state value of the response. So, the steady state value, it will cut the steady state value at a point from there drop a line perpendicular to the x axis or the time axis in this case, and this will be another point. These 2 points are important for us because you will have to measure what is the values it has. This is called L and this is what we call as T. Okay. Now, once you have the value of L and T, it becomes quite easy. So, then you just have to use this lookup table. Okay. Now, using this lookup table you can find out the controllers. Till this part whatever I have told can be done experimentally. Again, can I do it experimentally? Think about it. What am I asking you to do? I am asking you to find out the step response of the system, right. So, if you have to find out the step response of the system, you have the system with you. You just give step input to it and see what the output is. Will it work always? Think about it. Will it work always? You can pause the video and think about it. No, it will not work always, because there may be a case where your system to start off with itself is unstable. For example, suppose I give you an inverted pendulum. Okay. Now, what is an inverted pendulum? An inverted pendulum, if you put it like this, it has to be straight at this point, right. But will it remain straight in general? You have to move your fingers, right, then only it will remain in this inverted position. You have to balance it out, right. But suppose it is an open loop transfer function, that means you have no controller to move this your fingers, or suppose there is a cart attached to it, there is no controller to move the cart. Okay, then it will not be able to balance it, right. Okay, now who will move the cart? The controller will move the cart. The controller will tell the cart, oh, move this much, then there will be balancing, then move this much, then there will be balancing. So, the controller will have to do that action. Suppose you do not have the controller, that is the open loop case, right. Then what will happen? Even if you give step input to the system, it will just fall down, right. In that case, you will not be able to use this method. Okay, but what to do then, we will talk about that. Okay. So, let us take the cases. Suppose you can use this method and you can find out the step response, you find out L and T, and then suppose you are designing a P controller. Again, which controller should I design? It is up to you now. You have to take the call, what type of controller you have to design. How do you take that call? Suppose you have designed a P controller. First, you design a P controller always. Okay, you design a P controller how? What is the value of Kp that you took? You have to take the value T by L. Now, what is the value of Ti? Ti is infinity. Now, why am I finding Ti? Because Ki is equal to Kp by Ti. So, if Ti is infinity, Ki is 0, and if Td is 0, you see Kd is Td into Kp, then Kd is also 0. So, that is why this is a P controller. So, if you are designing a P controller, you start with a P controller, you design a P controller with T by L value. Once you give that P controller, check what is the output. What do you mean by P controller? Basically, this will be your P controller now. Now, once you see that, look at the response. Now, suppose the output has a steady state error. Okay, there is no problem with the oscillation phase. Suppose only there is a issue that the output there is a steady state error. Then you go for a PI controller. How do I find out the value? 0.9 times T by L. I know the value of T and L already, and Ti will become L by 0.3, which means Ki will become Kp by L by 0.3. So, you find out that value and that will be your PI controller. So, in this way you see, just by this is like a lookup table, you just have to find out the value of L and T. Once you know the value of L and T, you can just look up and use that value of Kp and Ki and Kd, whatever you are using, you use it and the system will work. We will show a demo for this. In this demonstration, we will perform PID tuning for the speed control of a DC motor using the Ziegler-Nichols open loop method that we have just now studied. Let's look at the hardware configuration. This is the same setup that we had done to find out the transfer function of the system. So, the DC motor is connected to the Arduino microcontroller via a motor driver, and the DC motor is the encoder pulses from the DC motor are being fed into the Arduino, which are being used to find out the speed of the DC motor. Now, the Arduino here will act as the brain of the operation, hosting our PID control logic, okay, and interfacing directly with the hardware. The PID control logic, the code written inside the Arduino looks something like this. You can see that here error is equal to set point RPM minus RPM. Here RPM is the measured RPM, and set point RPM is the RPM to which you want your motor to go. Then the integral controller's output is given by, or the integration operation of the I controller will be given by this code. Remember, this is a digital device, so everything has to be done numerically. Basically, integrations that you all know of will be done as summations here. So this is nothing but integral equal to error, previous error plus error into the sampling time. Ts is the sampling time here, and derivative is error minus previous error divided by the sampling time. Finally, the output of the controller is Kp error plus Ki into the integral plus Kd into the derivative. Now, this Arduino is then connected to the computer. In the computer, we have the MATLAB environment. From the MATLAB environment, we send specific PWM values to the Arduino to drive the motor at a constant level. Now, in the first step, what we will do is we will send a PWM signal through the driver to the motor so that it runs at a particular level, and that is your step response of the system. Okay, we will observe the step response, and then we will try to identify the system parameters L and T that are used to find out the PID gains. Let us look into that first. I am compiling the MATLAB code. So the MATLAB code will send the PWM value to the Arduino. So we are compiling the code. Now once the code has been compiled, now the PWM signal has been sent to the motor. Here is our motor, and you can see that will be the step response of the system. Let me show you again. You can see that is the step response of the system. Okay, so once we have the step response, we'll try to find out the value of L and T. And so here first task would be to find out the inflection point of this step response. The inflection point can be found out by differentiating this curve. Again, you have to do a numerical differentiation here. So you have to find out the point at which you have the maximum slope change. So that point, once you find out, that will give you from there you can find out the value of L and T, and these are the L and T values that we have found out. Using those values of L and T, we can find out the PID values. So then we move to case 2. Okay, this case 1 part was the part where we were finding out the step response of the system, calculating the L and T, and then finding out the PID values. Okay, you can see that the PID values are shown here. So I have already inbuilt it in the code itself. Once you find out the value of L and T, from there you can directly compute the value of PID from the table that we have. Now we apply the PID values we just computed to the DC motor. These two parameters will be sent from the MATLAB to the Arduino now. I am switching to case 2. So this is the part that will take care of sending the PID values to the Arduino. The Arduino is waiting to get the PID values. So the set point I am putting it to be 20 now. So that means I need a 20 RPM here. So I need 20 RPM. Let's see. You can see with the PID values that we have found out, the motor more or less runs fine. There is little oscillations here, but this works almost perfectly. So this is how you can tune the PID values for speed control of a DC motor using the open loop method. Now that you have seen the demo for the open loop case, now let us look at the closed loop case. So when do we use the closed loop case? For the example that I gave, the inverted pendulum example, it was an unstable system, right? So at first you have to at least do some bit of work so that it becomes stable, and then you can go for the closed loop method. Now what is the closed loop method? See, in the closed loop method, what is done is you have the system and you already connect a controller to it, a P controller to it. This will be your system. So now that you have connected a P controller, you can change the value of K. Now you keep on changing the value of K. Okay, keep Ki and Kd 0. We are not taking any value of I and D now. We are taking this K value and we will make it, we'll start small. We'll start from 0 and then we'll keep on increasing the value of K. Okay, then you increase the value of K till there is marginal stability. What is the meaning of that? You increase the value of K till the output has only oscillations. It should not be decaying, it should not be unbounded, it should have only oscillations, fixed magnitude oscillations. Go to that point, find out that value, we will call it to be the critical gain, okay, Ku. So, that is exactly the point at which you will have oscillation. You make it more than that, you will have you might have unbounded oscillations, and if you make it less than that, then you will have decayed oscillations or vice versa. Remember, from a root locus point of view, which is this point? Suppose you draw the root locus, you had drawn the root locus. Suppose this is an example, the root locus looks like this. Okay. So, now in this root locus, what am I doing? Basically, I am changing the value of k, right? At different points, I have different values of k. So, there is one point at which there will be only oscillations, and that is this point, right? So, the point at which the root locus crosses the imaginary axis is the point at which you will have oscillations. From a transfer function point of view, right now we are thinking that we do not have the transfer function. So, let us forget about this part now. Okay. Now, experimentally I keep on changing the value of k, and then I reach to a point when there is sustained oscillations. Fine, I got there, the value of k that I got is called Ku, and since there is sustained oscillation, it will have a time period, right, and that time period we will call to be Tu. Once you have the value of Ku and Tu, this is again a lookup table of this form. You can come up with the P, Pi, PID values, and this will be the lookup table, and you can see that everything depends on the value of Ku and Tu. Okay. So, if you are designing a PID controller, then take the value of Ku, multiply it with 0.6, that will give you the value of Kp. Ti will be Tu by 2, but then here from here you can get Kp by Tu by 2 will be 2 Kp by Tu will be your Ki, and similarly you can find for Kd also using this. So, finally, you have the value of Kp, Ki, Kd, and this will be the controller that you wanted. So, this is the tuned controller that you have. Let us look at a demo. In this demonstration, we look into the DC motor position control PID tuning, and here we will be using the closed loop method that we have just now discussed. Recollect that in one of our lectures we had found out the transfer function of the DC motor when we were considering position or angular displacement of the shaft as output and the voltage across the terminals of the motor as input, or the armature voltage as input. In that case, we found that the system was a third order system and it was a type 1 system. And if you draw the root locus of a third order type 1 system, you know that it will always cross the imaginary axis. That means we can expect that in the closed loop case, for some value of k, we would be able to find out an oscillation. Okay. So, let's check that, and using that critical gain oscillation and the time period, we will try to find out the PID values and use that for this setup. So, here also we have two cases. The first case here is the case where we are trying to find out the critical gain or the ultimate gain Ku. Okay, this is the gain at which we will have oscillations at the output. Remember now that the output is position now, no longer speed. Okay, the output is position, and now I will give a value of Kp as 5 and then keep the value of Kd and Ki 0, and we will see how the output looks. The hardware setup is similar to what we discussed for the open loop case. So, there is no change there. Only thing is that now we have the controller in the loop, and you can see that in this closed loop setup where your k value, the gain value was 5, this is the output. You can see that if you go back, you will see that the shaft of the motor rotates a bit and then stops, because this is position control. So, basically we are saying that the shaft of the motor has to go to a particular point and then it has to stop there, and you can see that it does that. So, no oscillations yet. So, we will increase the value of Kp and see if we can get oscillations. So, no oscillations again. Initially there was oscillation and then the motor stopped. Let us go ahead and increase the Kp. Now you can see that it is oscillating. Important thing to note here is that you will not be able to see the oscillation of the shaft here, because you can see the amount of oscillation is somewhere like plus minus 1 degree, about the 5, not even 1 degree, less than that. So on the shaft you will not be able to see that, but actually on the video at least this will not be clear, but when you see the shaft, the shaft is actually vibrating, and that is the reason that you are getting these oscillations. Okay, so these are the oscillations, and you can fine tune it, you can decrease and increase a bit, but let us consider this to be oscillating, although you can see that there are some places where there are damping a bit. So you can increase the value of k a bit more and check also. Okay, so I will fix it here, and now so if I consider this to be my critical gain, I'll try to find out tu, the time period, and for that I will need the zero crossings so that I can find out the time period. So we will find the zero crossings. Again, a code has been written to find out the zero crossings. You can do that on your own. So we'll find the zero crossings now. You can see that the zero crossings have been found out, and accordingly the time period has also been computed. The code is already written to give you the PID values. So you can see the PID values are written, has been computed already. So this is the table that I had shown previously for closed loop case. So once we do that, now I am switching to case 2, where I will be using these PID values, and you can see that the motor is going to 5 degree here. Okay, it's a very small angle that we are showing. So you can go ahead and check for higher angles also. This should work. You can see I'm making the angle 20 now. So my set point is 20, means I want the shaft to go to 20 degree. Have notice the shaft, so it moves to 20 degree. Okay, and then settles there. Again for 30 degree. See, it rotates to 30 degree and stops there. Okay, so this is how you can tune for the position control case. So now that you've seen the demos, you understand how to use these methods for the open loop case and the closed loop case. Now in both cases we assume that we do not have the transfer functions. Okay, so suppose you have the transfer function, then what to do? So now if you have the transfer function, the first thing is that you see you can use the same method that you used for this part, the closed loop case. Okay, only thing is that since you have the transfer function now, you can find out the value at which the oscillations will happen directly using either root locus or the Routh-Hurwitz method. We will take an example and see how to do that. However, if the transfer function is such that the root locus does not cross the imaginary axis, you will not get a sustained oscillation. In that case, you won't be able to use this method. Let us take example and try to understand. So you see, again remember, we have taken two cases. One of the cases was when we did not have the transfer function. When we did not have the transfer function, what we did was we found out we had two methods. First thing, we have to check whether the step response of the open loop transfer function is an S curve. If it is an S curve, and then we go to the two methods, either open loop or closed loop. Which one you have to use? You have to take a call on that. Suppose I have to use the open loop transfer function method, open loop method. What is the open loop method? You found out the step response, from that you find out the value of L and T, right? I showed you what is that. You have to choose the inflection point, draw a tangent, find out the value of L and T, and then you use the lookup table to find out the value of Kp, Ki, Kd, whatever controller you are using. For the closed loop case, what you have to do? You have to close the system, make a P controller basically, and then you change the value of P from 0 to whatever value you have to keep on increasing the value, keeping the value of Ki and Kd 0. When you are increasing the value, you have to reach to a point when there is sustained oscillation. Only oscillations, it should not be unbounded, it should not be decayed, only oscillations. So once you have these oscillations, the value of K at which you reach that oscillation is called your critical gain, Ku. Why is it called critical? Because if you increase from Ku, then you will become unbounded. If you decrease from Ku, you will become, the system becomes bounded, or the system becomes stable. If you increase from Ku, the system becomes unstable. If you decrease from Ku, the system becomes stable, or vice versa also it can happen, depends on how the root locus cuts the imaginary axis. So, once you get the value of Ku, you know that there is sustained oscillation. So, that means there will be a time period also, that time period is the critical time period and we call it Tu. Using the value of Ku and Tu, you found out, you use the lookup table and from there you can find out the value of PID. In this entire method, there is nothing, there is no discussion of performance objectives, no overshoot, no settling time, nothing, no objectives were given to you. That is why you could do this. Next, the next case can be, suppose you know the transfer function. Now you have more control because you know the transfer function, you have many resources to pull off from. If you know the transfer function, you can directly go to the CSD app and whatever ideas we have come up with, use that and then get to a PID value also. If you do not want to do that, you can also directly do this by just using the method that we have previously done, the closed loop Ziegler-Nichols method. So, since you know the transfer function now, you do not have to experimentally find out, you do not have to experimentally change the value of K and reach to a point when there is sustained oscillations. Since you know the transfer function, you can find out the point at which there is sustained oscillation using the Routh-Hurwitz table or the root locus also. You find out the value of that point. Once you have that point, you know the value of Ku, you can find out the value of Tu also. I will show you how to do that in an example, and then once you find out that, you are good to go. Then you can use the table, Ziegler-Nichols closed loop table. Let us look at an example to see how do we do that. So, here you have a controller which is in unity negative feedback configuration and you want to track a step input, unit step or step input, whatever input you want to do. So, if this is your controller, so the first thing that we want to do is, see, there are no performance objectives. So, I can easily go for a controller. Now, which controller should I go for? Now, look at the steady state error of this. Since the open loop transfer function is this, the steady state error of the closed loop system would come out to be 6/7. Again, you have to go back to steady state error discussion and check how to find out the steady state error of the system. Okay. So, Kp is 1/6 in this case. Oh, remember this Kp and that the Kp that we are talking about are different. Okay. So, this is the position, let me write it as position, so that you do not get confused with the Kp that we are using. So, this is K position. Okay. So, K position or the static error due to position or step input is 1/6 and therefore, the steady state error is 1/1 plus Kp or K position in this case. Okay. So, 6/7. So, that means that the output will have a steady state error when you give step input. Now, you know that if there is a steady state error, what should you do? Which controller should you use? You have to use a PI controller because I have to bring down the steady state error. So, in this case, we have chosen the controller that we want to use. We want to use the PI controller. And since we want to use the PI controller, then the next question should be, do we have any specifications? No, we do not have any specifications, right, in this case. So, I can directly go for Ziegler-Nichols method. So, Ziegler-Nichols method, let us go for the closed loop method. So, where we will have to find out the oscillations, value of K for which there are oscillations. When there is an oscillation, what is the idea? The idea was this, right? Oh, if this is the if this is the open loop transfer function, so you draw the root locus for this and then you can find out the point. Suppose where are the points? So, this will be the root locus, right? So, this will be the root locus. Again, I am drawing very roughly here. So, this will be the root locus. So, there will be a point on the imaginary axis, okay, where the root locus will cut the imaginary axis. I want to find out the value of K at this point. How do we do that? We can do that using the Routh-Hurwitz table. How do I find out the point this intersection point? If you remember, we have to use the Routh-Hurwitz table, and from here you can see how do I write down the Routh-Hurwitz table. So, first of all you have to write down the polynomial, this polynomial, and what is that equation, and this equation was s plus 1, s plus 2, s plus 3 plus k equal to 0. I hope that all of you have already practiced Routh-Hurwitz lot of times. So, I am not going into details about this because I have already explained what Routh-Hurwitz criteria is. And then once you break this up, this will come out to be s cube plus 6s square plus 11s plus 6 plus k equal to 0. So, this will be the equation that you have. So, if you write down, so 1, 11, then 6 and 6 plus k, and then if you write down the complete the Routh's table, this is what you will get. Now, you see, when will there be an intersection? For there to be an intersection, I have to at this point, that means there are s plus j omega. If j omega is the intersection point, s plus j omega must be a factor of the polynomial and s minus j omega must be another factor. So, at s square plus omega square must be a factor of the polynomial. See, I'm going a bit fast in this part because we know how to, these things we have already gone in details as to how to find out the point of intersection of the root locus on the imaginary axis. So, this part has to go to 0, right. So, if this part goes to 0, then 10 by this equal to 0 means k must be equal to 60, right. So, when is there an oscillation? There is an oscillation when k will be equal to 60. So, once we have the oscillation, so at k equal to 60 we know that there will be an oscillation. So, at k equal to 60, what is the auxiliary equation? The auxiliary equation was coming out to be 6 s square plus 66, right. This is the equation, or s square plus 11, this is the equation. So, this equation at k equal to 60, this will be a factor of the characteristic polynomial, or the polynomial 1 plus gs hs. For this polynomial s square plus 11 will be a factor. So, that means what is the oscillation now? So, the oscillation will be, frequency of oscillations will be, because what does this mean? S square plus 11 being a factor means s equal to plus minus j root over of 11 is the are two closed loop poles of the system at k equal to 60. Remember, this system has 3 closed loop poles for different values of k. At the value of k equal to 60, it will have 3 closed loop poles. 2 of the closed loop poles will be plus minus j root over of 11. Now, what is the meaning of that? This will be your frequency of oscillation, root over of 11 will be your frequency of oscillation, and this is what will give us our Tu. Remember, this is your Ku now, critical gain, and Tu will be 2 pi by root over 11, that will be your Tu. So, once you have the value of Tu and Ku, you just have to go ahead and use the lookup table for Pi. You have the value of Ku, you have the value of Tu, from there you can find out Ti, and then Ki will be equal to Kp by Ti, and if you do the calculation, these are the values that you will get. So, what I urge you all, after this I am not going to do the simulation part for this part, you have to go through the simulation. So, why do not you take this as a task? Make a Simulink model of the firm where you have a PI controller, and then you have your system whose transfer function is this, make the value of Kp 27, make the value of Ki 17.10 and see what the response is. Okay. Or you can write down a code as well. I mean, by now I am hoping that you know what to do. So, basically what will be our final diagram? Our final diagram is 17.10 by S plus 27. This is our controller. Then we have GS with us, and then since this is an unity feedback controller, unity negative feedback controller, this will be your final system. So, this you have to simulate, and I am asking you to simulate this and check what is the step response of the system. Okay. Now, if you take another question, say for example, this is another question. So, again we have the same question. So, we want to design a controller so that we want steady state error to be 0, because for step input I know that this system will not have steady state error 0, this is a type 0 system, and for this system we will not have steady state error 0. So, we want that the steady state error should be 0. There is no other specification given, only steady state error has to be 0. So, I know that I have to use a PI controller in this case. So, now can I use the closed loop method that we have seen? So, if you look at it, if you go through the Routh's table, the Routh's table will look like this, and see the only value at which you will have a root at the origin is when k equal to minus 6, right, and at that point the only root will be on the origin. Okay. So, in this case the meaning of this is, if you go and draw the root locus for this, what will be the root locus like? So, this is at minus 2 and this is at minus 3. How will the root locus look? So, the root locus will be something like this, you see, the root locus will be something like this. So, you can see that if the root locus is that, you can see that if this is the root locus, this is never going to cut the imaginary axis. So, if it does not cut the imaginary axis, I will not be able to find out a value of k at which there will be sustained oscillations, which means that the closed loop method I cannot use. However, the good news is that if you take this system and find out the step response of this system, it will come out to be an S curve. Okay. And using that S curve, you can actually go ahead and find out that inflection point, find out the tangent, use that L and T value to find out the value of the PI controller. So, this is how you can, you see, I mean this example shows you when to use which method. Okay. If you know the transfer function, then also you can take a call as to when to use which method. Okay. So, what we have done is we have seen different methods by which we can tune the PID controllers. Ziegler-Nichols open loop, closed loop method. If it is an S curve, we can go for those two methods and we can find out the PID values. If we know the transfer function, also it helps us, because if once we know the transfer function, we have these, we can use all the methods that we have in our disposal. Like for example, we can use the Routh-Hurwitz criteria, and using that we can find out the point at which an intersection is happening on the root locus. Okay, and that point will give you your critical gain, and then from there you find out the TU value from the auxiliary equation solution. So by that also we can solve the problem. But if you are not able to, for example, for this example, the example that we took just now, in this case there is no way that the root locus cuts the imaginary axis, then you have to go for the open loop method. There will be cases where you will not be able to get an S curve maybe, okay, then you might not be, you will not be able to use this method, okay, then you will have to do, you have to check what, you have to try to find out the transfer function of the system, then using the transfer function you will have to use the CSD tools and then maybe find out the PID values or tune the controllers. Okay, there are toolboxes in MATLAB which are called PID tuners also, which will helps in tuning the PIDs, but we will take those things up sometimes later in these lectures when I bring everything together, maybe at the end of these lectures. So when I bring all the things together, I will try to get to those apps as well. Okay. So for now we will stop here, and then in the next lecture we will also see some more demos and see what are the practical problems that are generally faced when we try to implement PID controllers. Thank you.